So how many of you like money? Yeah, so I like money too. We should hang out, idiocracy. But that's kind of why I'm going to do this talk here on discovering bugs or vulnerabilities using IDA. And I'll explain why in particular I choose IDA over the other reverse engineering frameworks and disassemblers out there. So anyway, in short, I live in Berkeley. I don't know why that's relevant, but I felt like putting it there. SANS fellow and curriculum lead, as Ed had mentioned previously. I've been teaching for SANS since I think 2006, which is crazy. And I took Ed's 504 class with Ed in Monterey, California back in 2004. So long, long time ago. It's amazing how time flies. So exploit dev summary, I just put this up here to kind of give you a little background as to where my expertise lies. I primarily focus on Windows vulnerabilities. And to be completely frank, that's where the money has been, right? So I'll mention some of the price tags that come along with these vulnerabilities, but I've discovered over 30 browser-based vulnerabilities, including Chrome as well, primarily though Internet Explorer and Edge, a few Windows kernel remote code execution bugs, exploitable vulnerabilities, products like BlackBerry, Juniper, Gatekeeper, many others out there. I was lucky enough when I was working at a couple organizations where that was my full-time job, was to do product security testing and look for vulnerabilities and then disclose them privately to the organization. So it got me a lot of experience, which is fantastic. Ed already mentioned the courses I've been involved in, and I'm one of the authors of the Gray Hat Hacking series as well, if you've heard of those. So this is kind of the first time you look at IDA. Everyone has this response where you start getting glazed over and imagining a video game or something like that going on. And that's the one that IDA makes me think of. So what is IDA Pro? It's a disassembler. Per Hexrays, who is the company who makes this product, it combines interactive programmable multiprocessor disassembler coupled to a local and remote it's a disassembler, and it's got debugging support, but that's the fancy definition from the vendor themselves. The current version is 7.4, and with IDA 7 that came out a couple years ago now, which is, again, time flies, it was a complete rewrite of the underlying API, which meant that all the plugins and scripts on IDA 6.9.5 and prior were suddenly broken, which requires people to go back and port this stuff. And some of it's possible, some of it's not possible. So that's why a lot of us will keep a couple old versions of IDA around, since some of the scripts and plugins only work on that one. A nice thing about IDA 7.4 that just came out last month is it supports Python 2 or 3, all the way up to like Python 3.7. So they give you that choice, and you can easily flip the switch and go back and forth between the two. It's got amazing debug support. So I'm not going to sit here and argue about why Ghidra is better than IDA here and IDA is better than Ghidra here. Jamie Geiger did a fantastic job comparing the different disassemblers out there like Radar and Binary Ninja and Hopper the other day. But it's really, for me, it's familiarity. I've been using it for a very, very long time. And I hear people complain about the price, and I understand it makes complete sense. But to be fair, this is an enterprise application. This wasn't meant to be something that's open sourced and home users just for fun tinkering around with. They do give free versions and demo versions that you can play with, but that's not their target audience. And I would compare this, it might not be a great analogy, but look at how many of you use Microsoft Office Suite, right? Why do you use that instead of LibreOffice? Yeah, there are reasons. But hey, it's free. Why are you paying Microsoft? It's the same kind of argument. You get support. You're getting enterprise support. You're getting a much more mature product that has a fantastic UX design. I mean, arguable, of course, but for a lot of us, again, it's familiarity. Everyone I know in the research community who I've been working with for years at VMware and Google and Microsoft and FireEye all use IDA. And I'm not poking at any of the other ones, especially Radar 2. I mean, it's a fantastic open source tool that's gotten a lot of love and a brilliant community out there. And then fantastic of the NSA to release Ghidra. But yes, it's expensive. But the debugging is where it really shines. And I'll talk about that a bit too as we go forward. So IDA overview. This is just a screenshot of IDA without the Donkey Kong reference here. And you've got on the left, I know the projector is kind of weird, wonky over here, but that's the functions window. and IDA has always worked well with the Microsoft Symbol Store, and Microsoft's been very generous to us over the years because, not necessarily because they want to give us debugging symbols, which is nothing more than the names of the functions that you see over there on the left, but because they have to allow developers of Windows applications to be able to debug their software. So for example, if you were to try and debug some of the DLLs with the Microsoft Office suite, you probably won't get all of them, and that's because you don't need them. So they're going to give you what you need. But what you see over there on the left at that spot is the function names window, which is extremely useful because if you don't know the name of a function, it's just going to give you a memory offset. And that makes life a lot more difficult. Now there's cool technology, and Ghidra supports this as well. It's called Flirt and Flare, which is the ability to identify patterns in statically compiled code. So we don't typically statically compile our code because it makes it unnecessarily large, and it also means that if a DLL or some module or function that you've statically compiled has a vulnerability in it at some point, well, you're going to have to go and recompile your code. And now there are versions out there that have the vulnerability compiled into it versus being dynamically linked. But this technology like Flirt and Flare can go in and identify patterns. It's almost like an IDS signature matching traffic that's seemingly malicious. But here we're matching patterns that are unique, and hey, that's the function malloc. So we can color code that and say, don't bother reverse engineering malloc because, well, unless you're crazy, you don't need to, right? So the main window here is the disassembler pane. That is called recursive descent disassembly. Recursive descent means that IDA understands when you reach the end of a block of assembly, then there's typically a condition like jump if not 0 if we're doing a string comparison or other. How do we determine whether or not to go one route versus another? And this information is stored in things like flags registers. I'll kind of show you a quick example here if I can. So this is, I've got a couple instances of IDA running, and this one's on Windows 10 with IDA 7.4. But this guy right here, this is urlmon.dll, which is a big DLL on Windows. And that right there on the screen is one function. Looks kind of like a circulatory system of a function, right? But it's one function, and all those white squares and rectangles, those are blocks of code within that function, which you can zoom in and see the disassembled code inside of it. Well, I just want to show you a quick example. If we go over here to the imports table, and the imports are functions that are dependencies. So DLLs and object files like binaries, they have dependencies on modules that we load into memory, and then we can link the functionality from those modules. The analogy I always give in class is, if I was going to come over to your house and cook dinner, I would bring the ingredients with me, but I typically don't bring a stove and chairs and everything I could possibly need to make the meal because I assume you already have those things on your system, in your environment. So these are where the dependencies of this module are listed. So I'm quickly going to search for a function called heap_alloc. Just sort this by name. So right here, and I'll look at the cross-references. We'll just go to a random one. Now see right here it says call heap_alloc, imports heap_alloc. It's a dynamically linked function. And all I wanted to show you here is look 2 instructions below that. It says test RAX RAX. RAX is a 64-bit accumulator register on the Intel processor, and it is checking to see if the result of that memory allocation call was successful. A test instruction does a bitwise AND operation. It's like a Boolean instruction. And it's checking to see if the result is a 0. If a result is a 0, that means that the call to heap_alloc was unsuccessful. And look at the instruction below that. It says jump if 0. If what was 0? If the result of that Boolean was 0. And that's going to send you one direction if the memory allocation was unsuccessful, versus if there is something in the accumulator register, then it's going to set different flags. We're going to take a different path and continue operation. So that's just an example of looking at some disassembly. And how do you get better at this? You just do it over and over and over and over and over again. So some other screens, we looked at imports, we looked at the function's name, we looked at the main disassembler pane. At the bottom there, you can see it says Python, very bottom. We'll talk about in a little bit here since it's the point or purpose of this talk. So what is disassembly? I know Jamie talked a bit about it the other day, but on the left there, you see ones and zeros, because you hear everyone say it's all ones and zeros. But when we think about opcodes that are executed by the processor, that is hexadecimal that we're typically looking at. But unless you're a binary ninja yourself and you can just bang out opcodes off the top of your head, then looking at the mnemonic representation or the instruction associated with that opcode is going to be much more realistic. So you can see on the right, those are the instructions that those opcodes disassemble to. For example, the infamous noop 90 opcode. Then we go further, and you've got decompilation. Jamie again mentioned this with Ghidra. So on the left there, you see a function, and I've intentionally put some white space in there because I have a question for you in a moment. But you've got the disassembly over on the left, and then on the top right, you've got the decompiled code if you've got the HexRays decompiler or a different one. And on the bottom there, you've got the original source. So you can kind of see the above and below how good of a job it does decompiling the code. Now, Jamie also said yesterday, it's a lot easier to read what's on the right than what's on the left. But if you don't know how to code, what's on the top right there, it's not very helpful. Right? It doesn't make much sense. And an interesting fact, and I can say it's a fact based on empirical data I've collected over the last 15 years of teaching, is that there are a lot of people who do vulnerability discovery who have never worked as a developer or would never call themselves a developer. They'll say, I have some scripting skills, but I kind of came in the reverse way. Instead of learning how, I'm not saying me, I'm saying a lot of people, came through the path of reverse engineering first and doing crack me challenges and others, and learned how to read disassembly instead of reading high-level code. So they're much better and would favor what's on the left versus what's on the top right. But if you look at all that on the left and how much, when we decompile that, how much smaller it is, if you can read what's on the top right, you're going to be a lot faster. It is more efficient way of reading things. And you can go in and rename things and variables and such and types as you learn them. On the bottom there, again, is the original source. And again, you can see how close it is. Now, can anyone tell me by looking at that source code or the disassembly or decompilation what function that is? Yes? Jake? Does anyone else know besides Jake? I knew that hand was going to go up first. String length? Yep. ASCII to integer. It's an example of ASCII to integer. Right here, though, we can fight about this after it if you want. Right here, though, I just point this out to show you, look at the different way it's represented here. Over on the bottom left, you can see it says subtract hex 30. But if you think about hex 30, that's the number 0, right? But then over in the top right, 48 is 32. Well, what's 32? Is 32 a space? Or is 30 space? 32. 20 space, right? In hex, ASCII? No, 20. Which is 32. In decimal. I'm just trolling you. So, it's fun. But you see, you see 30. Well, 30 from hexadecimal to base 10 is what? 16 times 3? 48, right? So anyway, we'll get back to this. So IDA Python, it's a plugin. It's been around for a long time. Someone made a failed attempt to write IDA Perl at some point. I have no idea why. It's like an angry Perl guy out there. Like if you ever played Skyrim from Elder Scrolls in the throat of the world, those guys with the gray beards, that's the Perl people who tried to write IDA Perl. So it's more flexible than IDC, which is the native scripting language that HexRays came out with, which is a very C-like language. So Python just generally feels more, it's just easier to code in. And you can utilize C types and such, and there's great community support out there. So it's just a fantastic way to interact with the underlying API of IDA. You can interact with the input file, you can interact with the debugger, you can interact with the disassembler. Extremely powerful and easy to leverage. And there's a couple examples there on the slide here. Like if we want to know when we're going through and analyzing an input file, just to give you context or an example, Say you want to write a Python script that hunts for ROP gadgets. And a ROP is, of course, return-oriented programming. And a gadget is nothing more than a small sequence of code that ends with a return or a jump or some instruction that allows us to maintain control. So to do or to write a script like that, we'd want to look for the C3 opcode, at least as one example, which is the ret instruction. It's the opcode for the ret instruction. And when we find that opcode, we can iterate backwards, and we can check to see whether or not if we were to execute the opcodes above the ret, would it still interpret that C3 opcode still being as a ret, so it's a usable gadget. So we can utilize IDA-Python to identify where in the code segment are we currently. We can disassemble the code or check the bytes or whatever we want to do. We can identify what segment of memory we're in. We can walk to the next address. We can check to see what function we are a member of. We can just do pretty much anything that you could do with the mouse and the keyboard and your eyes, but with automation. So porting is something that's required. I've written over 100 IDA-Python scripts, and I still haven't ported them all. But you would have to port to IDA 7 because they renamed. I know you can't read that very well, but they pretty much, it was all one contiguous word like get mnemonic with no spaces or anything. But then they decided to lowercase everything and put an underscore between the words. Every single function they changed the name of, which is an annoying example of having to port stuff. It's very trivial, but annoying. But either way, you'd want to port it to IDA 7. It's time to move off of IDA 6. This right here is, I want to, we didn't get enough QR codes earlier. But binary diffing, my question is, can you spot the difference between the two? I'll give you a prize if you can. I'm trying to demonstrate the point, though, which is it's like finding a needle in a haystack. If you have two binaries side by side, and one's version X and one's version Y, and some code changes were made, wouldn't it be nice to have the ability to go in and identify those code changes at the block and assembly level automatically so that you can only focus in on what code has changed? And why do we care about this? Because security updates. Microsoft releases security updates, and it's funny, I'll give a shout out to Jamie here because I was in London last week teaching, and Microsoft they've been playing around with patch obfuscation a bit, but luckily they haven't really rolled it out. We thought they were. And with the whole cumulative update thing that Microsoft does, these updates are huge. Like some of them are, well over a gig. If you look at Windows Update 64-bit 1809 Windows 10 Enterprise, it's over a gig. These cumulative updates, again, are massive. So to extract those, a guy named Greg Linares wrote a tool called Patch Extract, and it went through the MSU and cabinet files and extracted thousands and thousands of files and folders and kind of prioritized which files you should care about because of their change date. And you would have to manually correlate or correspond the name of the DLL that's been fixed with some of the knowledge base articles from Microsoft to try to understand which one is associated with what patch that month, so that we can go in and do some reverse engineering on the patch. So getting to that point is time-consuming enough. And my shout out to Jamie is, just recently, Microsoft started introducing this whole patch delta thing, where they put, when you extract a patch, it's got an R folder and it's got an F folder, which means reverse or forward delta. And the idea is they want to decrease the size of the updates because they're so large. And if you were to look at a patch now, what used to be a full DLL, for example, or a driver file that is the actual patch file, is now named .dll, but it's not a DLL. It's just a really small file that's got some data in it. If you apply that properly, what it does is it takes you from the current month's Patch Tuesday update, that one file, all the way back to the RTM, when the beginning of that build came out for that version of Windows, and then you apply the forward delta, and it takes you up to the current patch level. So pretty neat, and I was talking to Jamie about this. He's like, yeah, I'm experimenting now. I've got a tool, it's almost done, and it will actually allow you to do that without applying the patch to the system, so we can more quickly do patch analysis. So fantastic stuff there, and I'm hoping that that comes to fruition and we can use that. So again, the difference, I've given you a ton of time now to look at this, so I would hope that you could have found it. Obviously, it's right there, somewhere inside that circle. This is demonstrating, again, the time saving associated with doing binary diffs and the fact that we need to keep up to date with how Microsoft does their patching so that we can continue to save ourselves an immense amount of time. And you might be saying, why did you context switch from IDA and random things over to patch diffing? Because when you're doing scripting with IDA, one of the best ways for you to find new 0 days is to understand how Microsoft patches things. And if you can understand how Microsoft will patch a particular vulnerability, you can script up code that will go and hunt for new instances of that vulnerability. And I can promise you it works incredibly well. Exploitation is getting much harder, as you can imagine. Unless you're in the IoT world, it's still pretty easy. For those who still miss Pearl Jam and Soundgarden and Nirvana, you can IoT all day long and get the 90s back. But you're not going to get paid so much there. I'll give you some examples. When I sold my first use after free bug, and that was back in 2011 or something like that, 2012, the number of buyers out there that would buy exploits were pretty limited. It was like iDefense would buy them, who was at VeriSign at the time. Now they're at Accenture. There was a couple places real close to this area around Bethesda and DC who would buy them on behalf of acronym agencies, three-letter agencies and stuff, and they'll give you a better deal. Or you can sell it to nation states. Like you could sell it to a proxy. One we all know is the Grug, right? He's a proxy working out of Bangkok, and there was a Forbes article years ago that had him sitting at the Dubliner pub in Bangkok with a big duffel bag full of Thai baht, and he had a martini. And the idea was you would discover some useful vulnerability like a kernel exploit or a browser exploit, remote code execution bug. You could contact him and say, I want the highest bidder. You're not going to know who the buyer, you know who the buyer is, but you're not going to know who the buyer is, and you just get some money, and he takes a commission. Those kind of buyers are out there as well. But when I sold my first bug back in early 2010s, I got, I think, $8,000 for it, and I was pretty excited about it. And it was a full remote code execution type confusion bug against Internet Explorer 8. And $8,000 was huge at that time. And then as time went on, you could get like $12,000, $14,000, $20,000. If you had a real good one, $30,000. Then in 2014 happened. And I remember Corland Coder, who's a good friend of mine, Peter Vanickow, I think we called each other at the exact same time because we both went to voicemail. And we were very upset because I noticed some Microsoft people in here. They introduced these new controls called deferred free, memgc, and isolated heap, and it like killed our exploits. It was such a strong mitigation, it knocked out like 90% of the use after free exploits. And it took money out of our pocket, not that they cared, but they're like, you're making money in an unorthodox manner, so we don't really care. But if you were selling a dozen of these a year, you're talking up to a couple $100,000. So why I'm saying this is what happens then is the price tag goes up. Now if you can get one working, like for example in 760 I introduced a new lab where we go through, Project Zero releases a lot of triggers, a lot of bugs. If you exceed our disclosure timeline, it goes public. And one of the ones from Ivan Fratrick that went public was a type confusion bug and a use after free bug. And you could combine the two together, and the use after free bug was an ASLR bypass, a memory leak. And you could use that to build your ROP chain using relative offsets. And point being that if you were to discover both of those bugs that Project Zero released and sell them as a package together for full ASLR bypass and code execution remotely, that one's now worth about $100,000. So the price tag goes way up due to the mitigations. Yes, it's a lot harder, but it's also worth a lot more money now. The kernel exploits, if you find a Windows 10, like 1903, 1909, 18, whatever, full remote code execution working exploit, you're talking starting price $500,000. And that's pretty much from any buyer out there. But you could easily get into the 7 figures with that, depending on your morals, on who you're going to sell them to. The world of Android and iOS, you're looking at starting price of $1.5 million for a remote exploit 0-click. I mean, and that's starting price, a crazy amount of money. So why binary diffing again? So we can find bugs. This is a screenshot of running a tool called BinDiff. And this is an easy example that's digestible for the short time we have, where I would say, okay, we do a diff, and up top is the unpatched version, and on the bottom is the patch version. And this is simply a block within a function within a DLL that has been patched on Windows 10. And on the top one, I know it's hard to read, but it says XOR, so 0 out, register 8, which is a 64-bit register. So we're zeroing it out, and you can see IDA has identified that as the DW flags argument. Well, when you look up the DW flags argument on MSDN, when associated with the load library call, which loads modules, that indicates something called the safe DLL search order. And on the bottom there, you can see that they are moving the value hex 800 into register 8. And that's the patch. That's all they did in that patch, was change the value that serves as a DW flags argument. Because that argument of 800 says the DLL can only be loaded from the System32 or syswow64 folder. It can't be loaded from anywhere else. As where the above option, the analogy would be you're in your kitchen and you want to use salt in your meal, so you go to the place where the salt is supposed to be, but it's not there. Well, on the bottom, then you're not having salt. On the top, well, you're going to go looking all over the place for the salt, maybe even the bathroom. That's why it would be dangerous. So in exploitation, if we can get something malicious DLL onto the system of the victim, then we can get potential code execution to work or to occur. So I've got some demonstrations. We've got about 8 minutes, so we'll see how many we make it through. That right there is my dog Ludo. You're wondering, why is my dog Ludo up on the screen? Because the bottom there, I'm going to mention real quickly, use after free bugs. And my analogy to explain that a lot of times was a bit grim. And it had, due to the fact that I had 2 dogs, and the one dog I liked, that one, and the other dog I didn't like so much. And he's still alive, thankfully. But my analogy would go and explain referencing and dereferencing and such, and how, like, if something happened to one of my dogs and I'm on the road and I've still got a reference, so that's homage to the dog there. But I'll change that analogy to a beer analogy. Let's say that I'm away, I'm on a trip, and I'm a beer snob, and some of the beers I like are like just really hard to find, and they don't make them anymore. So you might only have 1 or 2 left, and after that they're gone. So let's say that you're on a travel, and I've got a reference to that beer. It's in my mini fridge in my home office, intentionally, and I'm on a trip, and some friends come over. My wife is hosting some people, and someone decides to drink my beer that they shouldn't have drank, and so my wife realizes, hey, his favorite beer is now gone. I'm going to go ahead and replace that. And let's say it was a nice Belgian beer like Westvleteren, it's just hard to get. And she replaced it with a Stella, which is the #1 Belgian beer. I'm sure you can ask Jeroen. Where are you? Are you in here? All right. It's a true statement, right? So the beer has been replaced. Now I have a reference to a beer that's not the right beer, but there is a beer there. So what's going to happen then? I'm going to be upset, right? So it's been freed prematurely because someone drank it. I go to use it. It's been replaced. It's not what I want. And what happens? I get angry. What happens in an application or a process? It gets angry and it crashes. But if somebody replaces it with something malicious, then we can potentially take over the process. So real quickly, finding deprecated functions. So let's go a little bit out of order. Since this one's up here, and this is the DLL sideload example, I'm going to go ahead and run an IDA-Python script. So let me go into this guy. And it's just called DLL sideload, and it's not going to run because I'm on the wrong OS. So that was a good example of a demo. Come on, thank you, appreciate that. So what just happened here? What's the lesson learned? Port your scripts before you do a demo on Windows 10. So what that was supposed to do, and I could probably still show it, but it parses through looking for the load library call, and it cross-references any calls to load library, and then it will go in and it will look at the DW flags argument to see whether or not it is a 0, or if the assembly that was going to execute would have resulted in a 0 serving as the argument. And it quickly does identify that that vulnerability does in fact exist, the one that we just talked through on the slide there. So if we have time, I'll go back to that one, but let me go ahead and run another one. How many of you are familiar with the infamous sort vulnerability that there's a format string bug in sort over the years? Anyone hear that one? Every year or two, someone would rediscover the sort vulnerability, and Microsoft refused to patch it for some reason. All they had to do was recompile it, but they didn't, and it was almost like they were trolling, and someone would post on full disclosure, I found a 0-day, and Microsoft went like, here we go again. No, it's the same bug. And Microsoft would respond and say, well, there's nothing you can really do with that bug. So what I'll do first here is just show you that bug, what it would look like. So we'll just run sort. If we do that, it comes back and says the system cannot find the file specified. But if we put a %x on the end, you can see we get some memory kind of being leaked out off the stack. And if we put another %x, we get another double word of memory, in this case is 0. Do it again. And we could just keep putting these %x's like that. You can see eventually the 7th argument, I believe, we're able to print off the 41414141 that we put in to begin with. So my demo here is to use IDA scripting to see how fast you could have found that bug and determine if it's vulnerable or not. So I'll go over here to IDA where I've got the sort executable loaded right up there. And we're going to run this ban function script that we use in 760. In the ban function script, if you want to take a quick look at it, if we go out here, just like Jamie showed the other day, he rewrote kind of a small snippet of this script for Ghidra as a demo. This script I wrote maybe 5-6 years ago, and those are a bunch of deprecated functions that should never be used. Microsoft identified them. They stopped supporting the ban.h header file, but they're still really good functions to look for. And this script will go and look for the presence of those in any binary input file, and if it identifies them, it will set breakpoints on them and list them all out, so that way we can go and try to locate them and see if it's a vulnerable condition. So I'll go ahead and try to run it inside here. So we'll do Alt F7 to bring up the script window, and we'll say ban functions. This one thankfully did work because I ported it. You can see that fprintf is used, and fprintf, the printf family of functions is problematic if you exclude a format specifier, which allows a developer to specify how they want data to be printed to the screen or written to the file or elsewhere. And in this case, you can see there's several calls to it. And if we click on one of them randomly, it takes us to the call location. So you can see right there, call fprintf. You can see a format specifier right there, the %s. So that wouldn't be a vulnerable condition that's causing this problem. Click on the top one here. You can see that there is no % format specifier above it. And you can see it's going to IOB, and looks like it's associated with some kind of an error message. So if we go ahead, and now that the breakpoint's set because the script set them, we can go into our arguments up here. Select the debugger first. We'll say Windows debugger. Again, this is one of the things that we support in IDA, which is not supported in Ghidra. So local's Windows debugger. Go down here to process options, and I'm going to specify parameters of a %x. Sure, it sounds good. We'll say OK, and we go and run this. And we immediately hit a call to printf. This is one that doesn't have a % sign associated with it. If we look in the background, you can see nothing's been printed onto the screen yet. If I hit and go say, let's go ahead and step over this, and now we look in the background, you can see right there the A's were printed out and then the memory address. Well, we can look on the stack here and see that same address is right there, which this ends up being the offset within kernel 32 of the get standard handle function. That is a reliable leak, which means that even though it's not an exploitable bug in regard to code execution, because Microsoft doesn't support the %n specifier, that would be an example of a potential ASLR bypass, because I know that the first thing that's going to be leaked out is the address of that function in kernel 32. So if I can identify the relative offset of that function within the kernel 32 DLL, and we reboot the system, the DLLs are randomized, they rebase, we could leak that out, and now we know where the DLLs were rebased to, and we'd be able to bypass ASLR that way. So I thought, maybe it's a bit careless to leave that thing around so long. In the 64-bit version of recent Windows 10, they recompiled it, and it got rid of that bug. But if you look at Windows 3.1, all the way up through Windows 10 32-bit, it's still there. Oh, wow, we have run out of time quickly. Let me see if I can show one last thing, though, before we wrap up here. So let's take a look at one other example that I think is interesting. This is Windows 7 here, and we've got Sophos antivirus loaded up. And I've talked about this in class before when I teach, but this one we can attach to the running Sophos antivirus process. If it's up, and you can see Sophos is running down there at the bottom, and we run the ban function script, and the ban function script identifies a ton of bad functions like stir copy. We've all heard of that one inside an antivirus engine. Look at all the calls to stir copy up here. And that's not stir copy with an N. So we double click on this guy, and you can see exactly where it's called. So now that we've got that set up, we could say, okay, well, let's go ahead and attach to the antivirus process. If we can find it here, we're looking for sav main, Sophos antivirus main engine. And if we find it, if not, that means we'd have to connect as, start this up as administrator. Anybody see sav main in here? S-A-V-M-A-I-N? Yeah, I think it would require that we run this as administrator. I can do that real quickly, and then we'll go ahead and wrap this up so I don't eat up any more time. But Ed said we did skip 5 minutes from the afternoon break, so. Right, Ed? Yeah, exactly. So let's go ahead and start up IDA one more time here as admin this time. So we say load IDA as admin. Come on and start up. UAC. Oh, that's the installer. All right, so IDA should come up any second here. There it is. And let's bring up sav main. Go. And we'll run that script again, the ban function script. And all the breakpoints should be set. Let me just double check. All right, they are set. And now we'll go ahead and attach to the sav main process if it's there. Anybody see it this time? Well, let's do this then. Sophos knows it's being put on a spot here. It's not very happy because he just got acquired. It's like, come on, don't mess with us here. There it goes. All right, so let's try that again. Let's see if the process shows up now. Let's go back, debugger, attach. One last time for the win, I hope, here. Anybody see sav main? Do you see it? $212? PID 212? 2212. Thank you, sir. There. No, that's sav admin service. It tricks me. All right. Well, I can't eat up any more time because we do have another talk coming up here. So I apologize for not being able to attach to the process. What was supposed to happen, though, was we would reach the breakpoint here, and just like we did with the sort example, and you would see that load library. So the DLLs that are loaded by the process use stir copy as far as the names are concerned. So it's a buffer overflow opportunity inside the antivirus engine that they never bothered fixing. So that would be the end. I'm happy to talk about this stuff afterward or at the FBI place and such. So I would say questions, but I don't think we have time unless Ed says we do. But thank you for your time. I appreciate it.